Good.
Okay. Perfect. All right. So shall I start?
Yes, you have the floor.
Okay, thank you. So good morning or good afternoon, everyone. This is a webinar about the EnRiMa project. Some of you might be familiar with it. This is a 4-year project that ran from 2010 to 2014 with 9 partners in 6 countries. We were coordinated through Stockholm University, and I work both at Stockholm University and UCL. Currently, I'm spending the year in Montreal, Canada. Okay, so I will give an overview of the project and outline its objectives, and then I will describe 2 of these modules that were the highlights of the project. And then I will talk a little bit about the integration of the energy management system and the potential for commercial exploitation that will come out of this project. So the objective was twofold in terms of the modeling features. First of all, we wanted to have better treatment of energy flows, and we also wanted to have treatment of uncertainty in electricity and fuel prices. So these were a couple of the features that we'd identified that were missing in previous models that were helping customers manage their energy consumption at the building level. And the impact in this case was not only to develop or to add these new features, but also to go to the next step, which is to try to integrate a decision support system engine to have more streamlined management of energy efficient sites, and to develop a graphical user interface that could be integrated more or less seamlessly with the user's existing ICT infrastructure. And then we could use that to validate what the decision support system could do. So we developed these features, we implemented them at 2 test sites, and then we did this recovery of investment analysis to show that by using these decision support systems, we could actually reduce energy consumption both in the short term and in the long run. And through this nice graphical user interface engine, we could go some ways towards commercial exploitation, because it would serve as a proof of concept that this kind of smart building energy management system could be effective, and it could integrate well with what the customer already has. This is an overview of the functionality. I won't go into too much detail, but basically what we were doing was we were taking data from the building about, for example, the thermal and electrical loads, as well as the external features of the building, for example, the U values of the walls. And then we were taking also external data, for example, about energy prices, weather, and the installed equipment. This was going into a database management system. And then we were doing our own analysis about the energy flows. So we're coming up with these Sankey diagrams that show the relationship between the inputs of energy and the outputs of energy, and what the effects would be of any retrofits. In order to handle uncertainty, we had a feature for forecasting to generate scenarios from analyses of electricity prices and the loads of the customers. So after we had all of these data, we could then embed them in the decision support system by running an optimization problem. So we could have an optimal dispatch of the installed equipment, as well as to undertake retrofitting decisions in the long term, and also to take into account the financial position, that is the risk exposure of the site. And this would all be usable through a nice graphical user interface, which would connect with the building sensors as well. And then we would do some kind of assessment to do a recovery of investment analysis to show how this technology could be deployed, and to validate its savings in energy consumption. So there would be this cost-benefit analysis that would look not only at energy consumption, but also at CO2 emissions and risk management, and also get some policy insights. And this would all be underpinned by a dissemination and communication campaign. This is just how the different work packages were connected. I think it's not so important for this talk. Here is something a bit more interesting. These are the laboratory and test sites. So at the bottom, we have the Cubic facility at Tecnalia in northern Spain. This is where we were able to test out how our thermodynamics model was working before we went to a real building. At the top, we have the two real buildings at which we implemented our decision support systems and were able to verify that using it would reduce energy consumption. So on the top left, we have the facade building. This is in outside of Oviedo, Spain. This is a center for handicapped people. On the right, top right, we have a technical university, technical college in Austria, in Pinkerfeld. So these are both buildings for public use, which was part of the requirements for this project, that we had to implement this at public buildings in the European Union. And I mentioned that we have two kinds of models. This is sort of how they fit together. We have an operational module, so indicated by this oval here. So this consists of how you would operate installed equipment over the next day. So this doesn't take into account any retrofitting decisions. It just comes up with a smarter way of using the thermodynamics of the heat flows in the building in order to manage your current energy system better. So this is what we call it kind of lower level decision variables. This is meshed. This could be meshed with a strategic module. The strategic module is for long-term analysis. This is for when you want to figure out, okay, over the next 10 or 20 years, how am I going to install new equipment? How am I going to decommission existing equipment? How am I going to make retrofitting decisions for the lighting or for the building's exterior? So these are the strategic decision variables, and they have some strategic constraints, and how they interact with the operational module is through the energy balance constraints, because if you want to figure out how an investment is going to perform, then you need to know how it will interact with the daily operation. So we need to have some representation of that. So anyway, I will talk about this in the next few slides, but the operational module is how to run the installed equipment better. The strategic module is how are you going to upgrade the existing equipment over the long term, taking into account uncertainty in energy prices and loads as well. Okay, so here is an overview of the operational module. So like I said, this is for the short term, and what you're trying to do is to take into account how the temperature in a given zone or a given room is going to be updated from hour to hour. This is one limitation of existing decision support systems that we'd identified. What they assume is that there is a given energy load in every hour, and you have to figure out the cheapest way or the most cost-effective way to meet that energy load. So in effect, they're assuming that the energy load is exogenous. It is somehow data or a parameter that's being given to you, and you either have to meet it one way or the other. But in reality, that's not the case. If you talk to a building energy manager, he or she is not going to say, I need so many kilowatt hours of energy. He or she is going to say instead, I need to keep the temperature within a certain zone in the building. So that's the way we approached it, is by assuming a way that we know what the loads are going to be, and instead just assuming that we know what the user's comfort requirements are going to be, and then figuring out how the temperature is going to be updated on an hourly basis. And we have a rather simple thermodynamic model, but we think it's still better than what was out there in the existing decision support system. So what we say is that we try to link the temperature in the zone to the heat from the radiator. So there's heated air coming out of the radiator, which in itself depends on the temperature of the water coming from the boiler and how fast it's flowing. The temperature in the room is also going to be affected by internal loads. So the more people that you have in your building and working there, the more internal loads there are going to be. It's going to be affected by the solar gains, which depend on the kinds of windows you've installed, as well as the external temperature and how sunny it is outside, and also through the U values of the building, so the external temperature here. So This is a highly nonlinear model, but we try to embed it in an optimization framework. So what we do next is we have this operational module, so we can run the decision support system, which will tell us what are going to be the set point temperatures for every hour of the next day for this building's heating requirements, while taking into account the thermodynamics of how energy flows around the room. And this can be affected also by what we call upper level operational decision variables. So these affect where you get the energy from. Okay, so this allows us to change the purchase and sales decisions of the site and to see if it will make any difference to the energy efficiency. So in a very abstract sense, here is the optimization model that we're solving. We're trying to minimize the energy trading costs and the technology operating costs, subject to some upper level energy balance constraints, technology capacity limits, and storage and energy trading limits. And then the lower level constraints, which are the temperature update and bound, like I mentioned, as well as flows on the radiators and the HVAC equipment. So this is a highly nonlinear optimization model. Since we're doing it for the next day, we assume that we know all of the external temperatures and solar radiation and internal loads with certainty. So it's a deterministic nonlinear optimization model. And this is what we find when we run it. So this is for Facade, the Spanish site. And we ran several scenarios. I'll mention what they are later, but the more important thing here is the two cases. So FMT is the fixed mean temperature setting. So this reflects how building energy management systems currently work at these kinds of facilities. What they say is that, look, depending on what the outside temperature is going to be, or depending on the time of the day, I want you to get the temperature to be a certain level. So, for example, at this site, since in the morning there's not that many people up and around, it's okay for the temperature to be about 20 degrees or so. Then after 9 o'clock, when people are active, you want the temperature to be, so this is for a winter day, so you want the temperature to be around 23 degrees until people are not active anymore, and then it goes back down. So this is for the 24 hours of a particular day, where the blue line here is the external temperature. So what this does is it gets the temperature to be exactly the level that you want, and it stays there until it goes to the lower setting. So this is how a traditional building energy management system works. This setting OPT here, so this is what we did on the right-hand side. This says that, look, we don't need the temperature to be exactly 23 degrees during these hours. The temperature can vary from, let's say, 21 to 24 or and a half or 25 degrees. So this gives us some flexibility, and using the solar gains that occur over here when in the early morning. So we don't need as much heating. We don't need to consume as much energy for heating here in the early morning, because we can sort of ride the solar gains and then stick to the bottom level of the temperature band. And then as it gets warmer, we can sort of turn off the heating equipment and ride those solar gains further in the afternoon and save additional energy over here. Whereas what's happening here is that because you are forcing yourself to stick to one target temperature level, a lot of the energy that you had expended earlier in the day to ramp up the heating is now literally going out the window, because it's just going to get too hot. So because you were not able to sort of anticipate that's going to occur, you effectively waste a lot of energy with the traditional BEMS, and our smart BEMS, as we like to call it, is able to use the solar gains in order to reduce energy consumption. And this is sort of indicating what's happening with the heating and ventilation settings. So on the left-hand side, we are looking at the contrast between our setting in blue and the traditional, our setting in red and the traditional setting in blue. because you can see we're using less heat early in the day, and we're cutting down on heating demand in this late afternoon period that I've mentioned. Consequently, the demand for natural ventilation is also reduced. So we have almost no need for natural ventilation because we're able to anticipate what's going to happen later in the day, and then therefore keep the temperature within a comfortable range. Whereas with the static FEMs, you actually need to be ventilating a lot more. So the bottom line is that with the static FEMs, you are consuming about 700 kilowatt hours of energy for space heating demand, and it's costing you 42 euros every day, and you're producing 154 kilograms of carbon emissions. These figures are drastically reduced when you're able to anticipate what's going to happen and to run the energy system or the heating system in a more adaptive manner. Of course, these are just for the heating demand. If you look at the overall, the primary energy consumption, these figures are going to be not as stark. So instead of having about a 30% reduction in energy consumption, you'll have about a 10 to 15% reduction in energy consumption. We did another scenario, so the results for scenarios 1, 2, and 4 were not that different. Scenario 3 was a little bit different because this assumed that the government of Spain says that the zonal temperature, if the heating system is being used, has to stay below 21 degrees. So in this case, you can see that with the fixed mean temperature setting, the temperature, the most it can be is 21 degrees, and this results in a lot of energy savings, but still you are literally blowing some hot air out the window. With our setting, even though we have no flexibility here in the day, because we're able to anticipate what's going to happen, we can adjust our settings here early in the day and sort of later in the day, and still come up with 15% savings. So the government can come up with more ambitious regulations, which is going to make the current static building energy management system more attractive, but it's still not going to be as attractive as what we had even without the regulation in place. You can see with the regulation in place, you can have energy demand cut down to 558 kilowatt hours, but even without that regulation, just by running the system more intelligently, we're able to bring it down to 494. So that's kind of the bottom line, and we've had a similar pattern at the Austrian site at Fingerfeld. Again, this flexibility allows us to reduce the demand for space heating. Here, the reduction is not as great. It's about 7.5 to 10%, but still, without having to install any new equipment, just by running the existing equipment in a more intelligent manner, you can outperform the current building energy management system, even when it has policy support. So this is a summary of the energy and financial benefits. I think I mentioned that already, but again, we don't need to go into these details. So we came up with these models, and the models were working. So these case studies seem to be on the right track. Next thing that we had to do was to perform actual energy audits. So in this case, we had to get an energy auditor to come in and to verify that energy demand is reduced as a result of using our decision support system. So basically what we had to do was we had to make two additional calculations. One was that we had to verify the multi-zone to single zone calculations, because in the model, we're assuming that this area was just one zone, whereas in reality, any area of the building is going to have multiple rooms. So we needed some methodology to transfer the zonal set point temperatures to the room set point temperatures. And the other thing that we had to do was to normalize the base case days to the optimization days. So this means that we would run the building energy management system as it's currently installed on one day, and then we would come back on another day and run it with our decision support system. Now, unless we're very lucky, they're not going to be exactly the same kinds of days. One might have different temperatures outside, different kinds of solar gains, so it wouldn't be comparing like for like. So we need some kind of normalization to ensure that one energy management system is not looking better than the other one just because it happened to run on a warmer day and therefore needed less heating. So this is how we handle the single zone to multiple zone. Basically, we're sort of taking weighted averages of the rooms by their volume and then attributing the set point temperatures. So this is not central to my point. More interesting thing is these base case days. We need to have some reference days in order to compare the energy consumption over the observed days. And okay, so again, these are maybe details that we don't need to go into. This is more important. This is the assessment of the savings from the energy auditor at the Austrian site. So here we have the dates on which we performed the audits. So for example, on February 20th, we ran the building energy management system as it's currently installed, the business as usual case. And then a week later, we ran it at the same site, but using our decision support system. So the savings were about 8%, but the 2 days were not exactly the same. So then we need to use a regression model so that we can compare the two kinds of approaches, so that they are looking at more or less the same kind of external temperatures and requirements. When we do that, the savings are about 11.3%. We did this over a number of days, and on average, the savings are about 7 to 8%, no matter which way you look at it. So it was nice to see that what we had done as a model could actually be implemented at a real site and leads to verifiable energy consumption savings. Okay, so this is the extent of the savings, and you can see the comparison of the business as usual reference day and the optimized day. Okay, next I will go into the long-term strategic module. So for this one, we're looking at the time horizon of 10 to 20 years, and we want to run the decision support system to do this what-if analysis so that we can get also some policy insights. So we can see how the site is going to adopt new technology, and then if we are looking at it from a policy perspective, we can also see, well, what kinds of regulations do I need to implement as a policymaker so that I can induce investment in desirable technologies. Okay, so this kind of strategic model is promising because it can serve both building energy managers and it can serve someone in government as well who's studying the consumption of energy by public buildings. And this is important in a policy context because after 2020, public buildings are supposed to drastically reduce their energy consumption in the European Union. So since we're looking at the future, we also need to take into account uncertainty. So for that reason, we have we had to do an analysis of the uncertainty in the technology costs, the market prices for energy, and the loads. So we had to come up with some kind of scenarios as depicted on the left, and we had to look at some risk measures. So here we have a stylized density function of the costs, and we know that some managers in the financial sector, they're concerned about costs being in the upper tail. So they use this measure called CVAR, the conditional value at risk. This tells you what your expected cost is going to be given that you're in the upper 5% or 10% of the cost distribution. So we want to minimize that as well. So we not only want to minimize the expected cost, but we also want to minimize the expected cost given that the cost is going to be in the upper tail. So underpinning this this methodology was the energy balance constraints. So we're saying that if you have some demand, you can satisfy that demand through various means. You can go to the market and buy energy directly. You can buy energy in order to run your generation technologies. You can buy energy and put it in storage technologies, which can also be charged by your generation technologies, and you can also have some passive measures in order to reduce your energy consumption. So we had to have a set of equations that governed the transfer of energy from one form to another. So that's what was driving this whole model. And then behind the scenes, we also had the solver manager, which interacted with this DSS kernel. So there was this interface to allow data to be readily exchanged, so that if you're inputting data, it can then be sent to the solver. The solver can take the data and render it as it's needed, so that the optimization could be dispatched, and then the results from the solver could be taken back, sent to the interface, and then relayed to the user. So we had an automated way of handling data transfer, data input, and data output, which, as you will see in a little bit, is also something that's helpful in terms of taking this decision support system towards commercialization, because it's just one fewer thing that the user needs to worry about. Okay, so in terms of the findings, again, we implemented this for the two test sites, and this is the one for Facade, the Spanish site. In the first column here, we are indicating what are the costs and energy consumptions of the site if it continues to use the currently installed equipment and does not do any investment or retrofitting. So as you can see, it has a cost of about 3 million euros per year, and it has energy consumption of 40,000 megawatt hours, and it has 7,500 tons of carbon emissions. And here is its 95% CVAR. So this is the expected cost, given that the cost is in the upper 5% of the tail. So it's a risk measure. Now, if we allow it to invest, and by the way, these numbers in the first column, they correlate very closely with the observed costs and energy consumption patterns of the facility. So we know that the model is reasonably well calibrated. Next, we allow for investment to take place. When investment occurs, you can see that primarily CHP equipment, PV cells, and some solar thermal is going to be installed. It's going to reduce the cost by 17%. It's going to reduce energy consumption by 35%, and with a likewise decrease in carbon emissions, and a more modest decrease in the risk. So we can see the benefits of using this model in order to pick the right technologies in order to minimize the cost. When we allow for storage, there is there's slight improvement in both the cost savings and the energy consumption savings. And then we had a couple more settings with different kinds of policy measures that don't make that much of a difference. The only one that stands out is setting 3. In setting 3, we're saying that the Spanish government passes a regulation to reduce energy consumption by 30%, by 50%. So you can see that, yes, it is possible to do that. If the government passes this law and the building has to comply by it, it will reduce its energy consumption by 50%. However, it's going to result in a negative 28% cost savings, or costs are going to go up by 30%. So this is also nice from a policy making perspective, because now you can sort of trade off what's going to be the cost of the cost with the energy savings. You can see, okay, well, maybe this is too ambitious of a policy objective, because with a 30% increase in the energy bill, the sites are not going to go for it. The other thing to take into account is the kinds of technologies that are being adopted. And as you can see here, CHP is important across the board. So again, if you're a policymaker, you can see that, okay, if we want to get to 20, 30, 40% reduction in energy consumption, then it seems like CHP and storage are going to be important parts of this transition. And you would then have to pass perhaps regulation, or to make it easier for buildings like this to be able to install and operate CHP equipment, because CHP is a little bit different than a traditional kind of technology, because you need more sophisticated controls. And if these kinds of sites don't have the right support to operate the equipment optimally, then they will be hesitant to adopt them in the first place. Okay, then we ran a case with, instead of minimizing the expected cost, we minimized the expected emissions. The results were more or less similar, so I'm not going to go into too much detail. You ran a case when you're minimizing the risk. So you can get a slight reduction in your risk, but then your savings in terms of the costs are not going to be as high. So there's again a trade-off between the risk and the expected cost. So that's nice to observe. And then for Pinkelfeld, we had again similar kind of patterns of results. The savings here were a bit more modest. This is because this site, Pinkelfeld, was more recently renovated than the facade site. So here the scope for savings is slightly less, but it's still 15%. In the base case, goes up to about 24% when you allow for storage. Okay, so similar patterns here. We also had to do an energy audit here for this one, which we performed for the facade site in Spain. So in this one, the auditor carefully looked at the month-by-month consumption of the different energy types to make sure that they match with what they have observed. So our model is able to replicate the measurements that are being taken. And then the auditor found, after changing some parameters, that the scope of the savings in energy consumption is about 15%. So I think that's more or less in line with what our own studies had indicated. And this auditor also looked at what would be the impact of single technologies on their own on the scope for saving in energy. So solar thermal seems to stand out from those, but clearly it's better to have all these different technologies together. So we were able to verify the extent of the savings in energy consumption. Okay, so this is what I presented with the models. I think I'm reaching my time limit, so I'm not sure if I should continue with this, or we can just have a little bit of a discussion about the market analysis and potential for commercial exploitation.
Yes, Asaf, yes, if you need 5 or 10 more minutes, it's possible, of course, huh? As you prefer.
Okay.
Okay?
Okay, then I will just take 5 minutes to say kind of what we did with the integration. So let me just get back here. Yeah. So like I said, there was behind the scenes, there was this DSS kernel that was handling the data import and export with the web service. So not only sending data as inputs to the solver manager, but also getting the results from the solver manager and relaying them to the graphical user interface. So here's a mock-up of the schematics. Again, I won't go into too much detail, but just to let you know that this was much more complicated than we had thought. And this is what makes the whole thing work in a seamless way that could take it towards commercialization, because all these annoying details about how to handle the data, how to interact with the building's current ICT infrastructure, how to read data from web services that provide, for example, temperatures, external temperatures for the next day and so forth. This is all automated. Okay, so this is not very glamorous. This is not something that I would start the presentation with, but this is what bridges what we did with the market's needs. Okay, so that's why I put this in here, to show that this is complex, but it is necessary for the potential commercialization. We also did some cases with validation of the DSS engine. So this was done at the laboratory facility to make sure that the thermodynamic model that we had was working reasonably well. I won't go into detail. Again, this is more details about the services and tools, just to give you a flavor of how complex it can be. And then the end result is graphical user interface. So these are just screenshots from the mock-ups that we had. So as you can see, you can reproduce the same kind of charts. You can run different cases. So basically, the user doesn't have to do anything except enter, like in this lower left-hand screenshot, is to enter the desired temperature ranges for the next day. Okay, so that's all you do. Then you select your building, and then you hit run. And then it produces this kind of graph. which tells you what your set point temperatures are going to be, and along with the external temperature for the next day. So it's nice and streamlined, so the user doesn't have to worry about anything except what he or she is familiar with, which is the building and desired temperatures. And we did a survey with this, one of the partners in the project was Hidrocantábrico Energía in northwest Spain. So they had organized some stakeholder group meetings, and they had people coming to the meetings test out this decision support system, and results seem to be promising from this survey. So we think that that's on the right track. And in terms of the market analysis, in the project itself, we rated the DSS modules as being either 6 or 7, and we were trying to do these, undertake these efforts in order to take them to technology readiness level 7 or 8. And it's kind of a challenge because in the market, so this is a diagram from the Spanish energy efficiency platform. On the horizontal axis, you have the impact and simplicity of implementation. On the vertical axis, you have how fast the return on investment is. So the quick wins are here up in the top right-hand corner. So these are easy to implement, make a big impact, and they have a big return on investment. So things on the demand side, like energy efficiency, lighting regulation and control, and so forth. The more difficult ones are on the lower left-hand side. So these take more time to implement, and they might not have a high return on investment. So these are things like PVs, renewables, CHP, things that I mentioned before that could, over the long term, have a bigger impact, but they're quite complex to implement. So these are more things on the supply side. In the middle, you can see our building energy management systems. Okay, so this is sort of where our technology is sitting. I think it's in a unique position because it can tie together the demand side with the supply side, which is exactly what a building energy management system does. So it's important using this to figure out sort of where we are in terms of the needs of the market. So we identified who would be possible users. So there could be owners of real estate who can use this for operational optimization or to do retrofits, energy auditors, because as we learned after talking to auditors in our project is that there's no unified or standardized way to run energy audits. So something like EnRiMa could serve as a standard. Energy service providers who can then provide services to technology developers through the use. For example, one of the companies in our project was Technalia, who do precisely this kind of activity. And ESCOs, energy service companies, so these are providing services for customers, for example, to help them to reduce their energy consumption. So a service provider used to just sell energy to customers. Now, because of new regulation, everyone has to reduce energy consumption. How are these guys going to make money? Well, power companies are going to make money not only by selling energy, but also by selling services. So we think that this DSS could be another means for them to add to their services. And then finally, we had this use case with this company in Sweden that would use the DSS. I won't go into too much detail about it, but this is sort of the motivation for it, which is that in most buildings in the Nordic countries, you have an external temperature, and then the internal temperature is just set to be something specific, like 21 degrees. So this is an example of the static building energy management system. You can control how fast the water flows through the radiator system, but you cannot change the temperature of the heated water in the radiator. It's just fixed depending on the outside temperature. So by having the flexibility to change some of these things, we can reduce energy consumption further. And in terms of our offerings, we think that we can provide 3 kinds of technologies that could be taken forward for commercialization. There's the operational DSS and the strategic DSS, and also the integration services. So this is sort of like the solver manager and everything that it connects to. that we think also could have a position in the marketplace. We did some kind of preliminary market analysis to see what would be the market size in EU 15 countries. So these are based on epidemic models. So the blue lines are indicating how much adoption is going to take place over the next 10 years, whether there is some kind of outreach program or not. So the upper blue line is with an outreach program, the lower line is without an outreach program, and this is the floor space in millions of square meters that are going to adopt this kind of technology. So the top one is for assuming a 10% energy savings, the bottom one is with a 20% energy savings. So clearly, if we can verify that EnRiMa has 20% energy savings and we have an outreach program, those are the two factors that are going to make a huge difference in terms of the propensity for adoption. And then they did SWOT analyses for both operational strategic modules as well as the integration services. Again, I won't go into details, but kind of one last thing to mention is that we had some adoption mechanisms, which are stakeholder outreach events. So this was led primarily by the power company in our consortium, which would organize information sessions and try to tailor the offering for commercial uptakes. So they know the market, they can potentially develop the technology to use within the company to offer services, or they can use their position on stakeholder board groups to make other people aware of this. We also looked at follow-on projects, so we could, for example, try to have a Horizon 2020 project or to get some funding, other kind of technology transfer funding through the EU. This would minimize the risk that's associated with new business ventures because I guess, as you all know, a lot of new startups, they actually fail. So we want to secure funding in order to refine EnRiMa, tailor it more for the market in a well-defined setting. And actually, we did obtain technology transfer money through the EU's Regional Development Fund. So this is a project called InnoSpirit, and this is for technology transfer to Central European countries. And the objective of this is to do further validation and tests for EnRiMa, targeting test sites in Hungary. So buildings in Central Europe could be retrofitted using our technology. And 425,000 euros were already secured from the EU's Regional Development Fund. So I think this could have a big impact in taking the technology readiness level higher. And finally, we have some evaluation agreements. So this follows the approach of previous types of decision support tools. And we have some evaluation agreements with commercial entities and the public sector, which could also, once people start using it, they will want to use it more. Hopefully, that's our thinking. So we have some evaluation agreements with people. So this is an overview of the stakeholder outreach events. These are the different kinds of follow-on projects we either have going or have thought about. These are the commercialization activities in terms of the evaluation agreements. So these are the different entities who have signed up to assess our tools. Okay, so, and then here we have a sample business plan targeting the Spanish hotel industry. Where did it go? Yes, here it is. So I'll let you read that and the other business plans on your own. And I think I will just leave it here with a summary of what we accomplished and the expected impact of the project.
Okay. Thank you, Afzal. Thank you for this very detailed presentation. So I will now open the question and answer time. So if there is any comment or question from the audience, please raise your hand, click the button on your screen, and I will give you the floor. No? No question or no comment from the floor? Well, it seems everything was very clear and very complete.
Well, thank you. Yeah, and if anyone has questions later on, you can just email me. You have my email address on the cover page of the slides.
Great. Okay, so if there is no comment or question, you can close your presentation as well.
Okay.
And I will now give the floor to my colleagues from EeB-CA2. Sandrine, are you here?
Yes, I'm here.
Yes?
Good afternoon, everyone.
And Francisca. Okay, so
There, she's sick.
yeah, I give you the floor to conclude.
Yeah, okay, thank you. Good afternoon, everyone. So actually, I will just conclude the presentation of the webinar with just few information regarding our last project activities, since the project will end in January 2017. So we have some few activities which will take place in the next month. So first, we will be participating at the ECTP conference, which will take place on the 17th and 18th of November this year. This will be in Brussels. So we will be there. So if you want to have some information and if you have the chance to come also to the conference, then just walk by and then just meet us, and we will be more than happy to provide you some more information. Can I change the slide? Yes. Yes. Okay. So also within the ECTP conference, we will be organizing a matchmaking event in the afternoon of the Friday, November 18th. So this will take place from 1:30 to 4 p.m. in the afternoon. So this meeting is actually offering you the possibility to meet people, stakeholders from the ECTP conference mainly. And you will have the possibility to talk, to organize, to book meetings with other people which are also participating to the matchmaking events. So in the case you would like to find new project partners for new proposals, or if you want to find people for business, for instance, to find investors, so you can maybe book meetings during the matchmaking events. So because, within the frame of the ECTP conference, there will be a lot of stakeholders which will be there. So this is really a good opportunity to find maybe the right partners or investors. So if you want to book a meeting, so just go to this link, and then you can register yourself. This is free. So, the matchmaking event is free. If you want to participate to the ECTP conference, then you have to pay for that. You have some registration fees, but the matchmaking event is for free. So if you want just to participate to the matchmaking event, you just have to come in the afternoon of the Friday, November 18. And so, of course, you can register here, and you have until November 14th to register and to book a meeting. Then you have, our coaching service. At the moment, we are offering innovation audits. So if you are interested in, just you can email me or email to my colleague, and she will transfer the information to me. And so where the innovation audits are basically first a self-assessment. So I'm sending you a questionnaire, and which is, of two pages questionnaire. So one page is on innovation potential assessment, And the second page is on competitiveness potential assessment. So you have first to fill in this questionnaire, and then I will make the analysis and send you back a report. And then if you want to discuss the results of the report, we can book a Skype call or a phone call, and we can just make like a bilateral discussion if you're interested in. And this is also offered free of charges, so do not hesitate if you're interested in. And then still we have the linking group. So this is the ECTP linking group. So if you're interested to promote also your results and findings or participation to conference, please feel free to just be a member of the group and then just to publish on the group. And I think this is it.
Yeah, this is it. Thank you, Sandrine.
Thank you.
Okay, so this is the end of the webinar, so we will close it. Many thanks to everyone for your participation. And if you wish to attend any other webinar we are still organizing in the coming days and weeks, do not hesitate to come back to me and I will send you the information. Many thanks and have a good day. Goodbye.
Thank you. Bye.